All right. Hello, everyone. Welcome to the stream. Birds. Where are the birds? Where is my... Oh, wait. No cable connected. Let's fix that. Here. Can watch some birds while I give you the intro for today. Hello Dutch, hello Jordi. And who else is there? Hello 1 FPGA. Why no 25k? Is there... What? Is there a 25k? Don't tell me there is Tang Nano 25k. Hey Max. All right, this time we will try to convert bitluni, luniASM to FPGA, Verilog. Hey Tommy. To Verilog and design a real Twitter show again. It's quite cold outside. Yeah, it's small. What? I don't know. Is there a 25k? No, there isn't. Anyways, I show you what I mean here. Maybe we will witness the birds at least once. We have almost sunset again, so, or at least it's dark outside. The birds were flying in and out all the time. I hurt myself today somehow here, my nose. 20? What are you talking? 20? This is the first time I'm hearing about Tang Nano 20k. Tang Nano 25k. Wait. What? They're actually... No. Yeah, but it's a different form factor, is it? Somehow all the links are broken. Taobao. Let me check. Let me switch to... We activate it so you can still see the bird. Oh, there it is! There it is! There you go. It's Tang Primer. Yeah. No, I'm looking for... I have the Primer 20k here. Is it leaving? Yeah, there it is leaving. Taking the poo sack with it. So it's Tang Primer. Let's check it out. AliExpress. YouTube chat broken. Oh, wait. Here we go. I know what happened. I accidentally turned off Home Assistant. Let me log in. Oh, come on. 5. I will fix that. What is this? What is this? What was this? What was this? Oh, you're... Here we go. Now. Wait. Bird cam. Here you go. Here you go, bird cam. What's the form factor of that? Tang primer RISC V. It has a soft core, not soft core, an extra core in there. 5A. We can check the Tang Nano, Tang Primer 25K. Tang Primer. Wait. Ah, that's a small one. Tang Primer. Let's see. Wait, what is that? Oh, you plug that on top of that here? Okay, let me check. It has 1,000,000 SRAM bits. 18 by 18 multiplier. What's the clock speed? If it's faster. It's the first time I'm hearing about that one. What is the Tang Mega? What? There is a one at screen chat. Oh yeah. Screen chat. Wait. Yeah, I can. Screen chat is broken, so let me re-update it. No, it's still broken. Oh no. Shit. Let me try again. Here we go. No, here we go. It's fixed now. Every single time trouble with the stuff. Now this is not $30 for the device. The whole thing with the P-mod. Is this USB? Yeah, that's basic USB. Oh, with the matrix. That's hard. $28, so you're $60 per matrix tile. Alrighty, I'm sticking with. Oh wait, we were looking at that one. Yeah. Once I'm rich, I will make an LED wall like the one that was used at Mandalorian. That's not my professional job. Hey, Shifter. My profession is to entertain people on YouTube. And I'm a coder, so I have no clue what I'm doing here. That's the next. Oh, did I just see a bird? Did you see a bird? Was there a bird? I always hear like the chirping from the small birds. I can open up the window so you can hear it a little bit as well, maybe. I could hear the chirping of the small birds, and now they sound way more mature. So I expect them to leave the nest quite soon. Negative. So this looks like an expansion part for a PC. What are you doing with that? Mining bitcoins or what's 140k loots? It's sick. Lunicoins. Mature enough for a pilot license. Yeah. Yeah, sounds so. So, I don't know. I don't have ISLA order. Nice. Congrats on that. I would like to set up some sort of recording where I could actually capture how the small birds are leaving the nest. I don't know if they immediately know how to fly or they practice somehow. So how does that work? They must somehow like spread the wings first. $25K looks like a good form factor. Yeah, I mean, if you compare it to the 25, which has like the 0.1 pin pitch headers, might be easier for hobbyists because you don't need like special sockets for that. USB bird detector. Smoke detector device. I could actually start recording whenever I see some sort of activity there, or I could record basically everything and then see if something happened. Scan for that. I don't know. Maybe there are some features on some cameras that record stuff, but oh well. So what is it about? Today's stream is about this device, more or less. So this will be an ASIC, luniASM ASIC. Let me draw it here. We made this assembler on stream recently, and I want this. I want to put luniASM on ASIC. Yeah, I could stream it to OBS. I don't know if that has some features to record whenever something happens there. Oh, there was one bird. It will leave in a second. Here you go. You are my motion detectors, bird motion detectors. Okay, so I will use Verilog to construct basically our luniASM CPU and then transfer it to tiny tape out, which has like eight imports or in pins, eight input output pins, and eight output pins. And we need somehow to address. We don't have internal memory. It's basically not possible to put much in there. So we will use an external SRAM, and basically like this one here. That's an SRAM that I bought for the C64 project that we did before. And I also have here also have a flash, which is basically the same form factor, and you can use data and address are real with pinout or internal. What do you mean with that? So we have address. I will use like the output pins for control, outside bus control, and a parallel 8-bit bus. So we will have external latches basically to store like 8-bit of the address, and the address can have like 24 bits here. So we will latch in. We can like chip enable each latch and write 8 bits in. There it is back, the bird. And this will be basically more or less like 24 bits address to the SRAM or ROM or IO. And we can use like 3 bits and then 3 to 8 demultiplexer to basically use a chip enable to either read write to SRAM, read from the EEPROM. I don't think I will make it possible to write to EEPROM because you have to like set sequences send some sequences of bytes to be able to write, and you have to erase blocks and handle all that trash. That's probably too big for the tiny tape out. And you could also address like an IO expansion or whatever IO that you put there. Then we have a NeoPixel pin basically here for a display, two PWMs, 2 times for sound. Have also what is CAS and asynchronous column address strobe atomic write recovery time. Yeah, I will clock it so slow it wouldn't matter. There's like 33 megahertz clock rate for output, and input is 50 megahertz or something. So I will clock it accordingly, and then we will have like each time we write or read from SRAM or ROM or whatever, we need like to store the address here. But we could also, it's not, the design is not decided. We could have like a parallel address on the ROM side. So let's say we have like 16-bit ROM address. So we could have like more more birds. Basically a separate address cache for the ROM, and then whenever we read like code, we most cases will only change the lower byte of the address. That will like speed up things, maybe. You could never get the... Oh yeah. It's hard. I mean, there are like sequences, and I'm not sure if they're like let me check with the Winbond parallel EEPROM. So they have like sequences of bytes that you need to send, and I'm not sure if these sequences differ for each manufacturer, which makes it even more difficult, because you have like to basically put in your either store it somehow in your ASIC, how, or boot sector or whatever, how to write to the EEPROM, which is like even more difficult. So let me check this chip here, which will be 27C 512. Okay, here is the data sheet. So address lines, 16 address lines. This one is only 65K. Erase method. Two shift registers. Let me see. Maybe there is a method drawn how to. Here. Hashtag bird. And there it goes. Hey Kaspar. Hey cosine. So we are trying to make a design for the CPU on the FPGA right now that we will transfer to ASIC, and we're talking about the possibilities of the bus, and basically if this is like let me check, is this erase waveform? Yeah, if you need like to erase stuff, you need to send like these data bytes, and then if you have programming waveform, is there like a specific, must be a specific, yeah, you have the state machine. Wait, this is start programming algorithm. Verify 1 byte, whatever device failed. So it's way harder to program the EEPROM than reading it, so I would just skip it for now. 14 volts or 20 volts, 12 volts, what? All right. Yeah, so I found chips from when we did the Atmel thing, and what I found is I have the programmer. Oh yeah, totally. It will probably even read on 3.3 volts. I bet, I hope. Yeah, I will program the code with the programmer and then plug it in and run the code on the device. And I will basically use SRAM as this chip here. So I have SRAM and I have the yeah. So I have here, I have the flash and I have SRAM already here. What I ordered is the demultiplexer today. So we will have the chance to maybe address even more. Now we have, we could address with an 3x8, we could address what is that? Is this a chip? Jordi is everywhere. Jordi is taking moderating job seriously. Is this the multiplex? Yeah. What's this? 3-line to 8-line decoder. Yeah, I ordered something like that today. I think I ordered something like that. If not, then I could check. How do you know that number from your head, Max? Are you doing this professionally all the time? Do you have like your stuff always there? So yeah, and I think I should have some buffers or like some latches also. Yeah, 3 to 8 decoder. I should have some latches also, but I didn't find them today. It doesn't matter. What we would like to achieve today is start implementing luniASM. That needs some changes, I think, because we didn't take care where the stack is placed in the SRAM. Hey, Max. Oh, peeps are knowing their dim chips. Hey, Max. I'm fine. Okay. So when we Z80. So what we will do today is like transfer this ASIC and the CPU design to FPGA and then try to put it on tiny tape out. What I would like to achieve today is like starting to transfer the opcodes and maybe look into how we use the clock to basically process everything from reading an instruction, switching the instruction, then waiting or fetching stack, storing stack, and stuff like that. And we can use, we could attach already SRAM, external SRAM, and test it with a counter or something. But I will just start developing, and I hope that we have something productive next Wednesday, because the deadline is, I think, on Friday in 2 weeks. Yeah. Yeah, they found really big bugs today. Nice. Okay, so let's do it. We can use Lushy Labs thing. Doesn't it support? That's the chat. New new window. One D FPGA. It's for Tiny Tapeout 7. That's the next shuttle for Asics. Where you can, I don't know if you know about Tiny Tapeout. You can put a small ASIC design on one bigger ASIC and basically get it in 6 months back, and that would be like the first CPU design that I would ever make. And we designed like this CPU in one stream 2 months ago or something. Yeah, like the Rickroll thing. Duplicate webs. Huh? Where's I just need a new window. New window there. Okay. No. Yeah. Start Verilog on 10 and 20k use block RAM. Yeah. Yeah, we can do that. I will just create a folder for that. Let me check. I think I have ASIC. luniASM. Okay. The birds are active today. Last time they were more lazy. ASIC. Okay, how do I use where is it? Here. Is it up to date? Oh, it doesn't say that it supports 20k for now. Hey. Someone mentioned it's supported in Lashe. Or do I need to update it? What does it say? Is it up to date? How do I see if it's up to date or not? Install another version. Oh no, it's current, okay. Ah, okay. You checked? Okay, getting started. One Verilog file. Okay, let's create a Verilog file there. CST. How do I call the CST file? Okay. That's the wrong window. Yes, I trust the authors. Here we go. That was the wrong project. Can we zoom out a little bit? Okay. Getting started. That's text. Oh, constraints. Okay, here we go. 20K. Add from template, UART, HTML buttons, LEDs. Oh, we need start from scratch. I think I got the tools already. How do I link them? Verilog. Build and program. Here we go. Yeah, I have everything set up. Module top not found. Okay. I completely forgot how Verilog works. Okay. Should we do system Verilog? Oh, can I do a template? No. Okay. Let's do add constraints. Oh no! Add from template. Clock, LEDs, buttons, SD card, flash, UART, HDMI. Add constraints. Nice. Okay. I can remove that one. Huh? Cut or what? Huh? How do I remove it? Oh. Boop! There you go. So, that's easy. Store, then let's do okay. Let's start with Flashy Labs, learn, and that's the code. Tang Nano Series. It's the same. Let me zoom out a little bit. Getting started, all that. There must be a blink getting started. There must be a blink program here. Creating a new project. VCSD. Oh really? Today? Yeah, I might be wait, let's just copy that module top and then LED counter, and we will basically input clock, output LED, but we don't use buttons yet. Okay, let's do the always block, which is basically okay. Let's build and program. Let me connect that device. Here. And I hope I... Uh-oh, did I move the camera? I moved the camera. Uh-oh. They won't fly today anymore. Yeah, I need to Zedic first. Unable to open. Hey Fu. I think we need the Zedic here. Where is it? Where is Zedic? Zedic here. JTAG. My search is broken on my PC. I don't know what happened. I was shutting down my PC and now I can't use search anymore. This makes it harder to find Zedic here. Phew. How do I find Zedic on my PC? Okay, let's try Windows Device Manager. Yeah. Yes. Then I need to find the Windows Device Manager. when I type, maybe I need to restart. Let me restart Explorer. I don't know what happened, but because you need like maybe a license if you're not using the educational thing. You can always get a license. I just want to try that with Lushy. It's super cool. They have like this basic simulation as well, and it's using open source tools like Yosys, so I can transfer it directly to the Asic stuff, which also uses Yosys. Okay. Now let me. Nah. Oh, come on. How do I find settings here? Settings, control panel. But you can use, I always use GoWin. Last time I used the GoWin thing. That's the GoWin FPGA 1020K, 10 Nano 20K. How do I find settings in the Windows menu? This is terrible. Oh yeah, please, thanks. I don't know what happened, but it's really broken. Okay. Okay, so how do I no, right click, does it? Oh yeah, there is one. Yeah, you're right. So, which one is that? USB? But the device shows something. I don't know what it. Is this USB cable broken? It seems like it is. Let me switch the USB cables here. Yeah. Okay, let's see. Xilinx Altera? Yeah, it's very cheap. You can get a 20K for like on the board with HDMI for 30 bucks from AliExpress. And so where do I find it? You Xingong programming device. Hey, let me try again with the new USB cable if it's... Yeah, no. Okay. I have serial ports here. That's the one from the device. Yeah, it is. It is. So that's why I got plenty of those. The Tang Nano 9K has also, yeah, that one is only powered up, but it has also HDMI. Can use you can run an MS-DOS emulator on that one. Completely 9K for 20 bucks, I think, shipped or not shipped. I don't know. Not sure. But it's quite good for you know what, Zedic? Let me Zedic. Why is it? How do I find Zedic on my hard drive? It's not in the system menu. So let me find it. I want to do it as the way that it's described. Okay, there it's not. Can someone who has Zedic check in which folder it's installed, please? So I can find it. What's the company name or whatever? Because it's not, there is no Zedic folder in programs. what's the name? Akio. Let me check if I can find Akio in the system. I won't install it again. Okay, I might install it again. I just check and it's running, it's just running. No, it's in the download folder. Hey, unimposing, thank you very much. List all devices. Yeah, I just downloaded it. It doesn't have an installer. Yeah, probably 20k friend. So what do we change here? So JTAG. Debugger 0. Win USB. Okay. Debugger 0. Win. Here we go. C2 stand out. Yeah, I probably have Zadig in my archive DW colon and then tools or something, or software. Software, and there might be Zadig. No, it's not there. It's just in the download folder. Okay, let me check if it can do now. Uh-oh. I set the type right. Jason. No, 20k. Here we go. Shit. Constraints editor. Wait. Is this now wrong? Let me remove everything again. Add from template and then clock, and let's might need to save again. Okay, let's build and program. Up. Oh! Toolchain completed. Oh, wait, is this an error? Different I/O modes for the same bank were specified. Uh-oh. No. I want always this. Always 3.3 volts. Let me check. Yeah, that's the wrong. I think 20k is only experimental. You see that it uses 9C, which is wrong. It will probably not work Yeah. What's the issue? Yeah. Different I/O modes for the bank 3 were specified. SSTL 25. For which bank? I only have specified to. Oh. Huh? Did I miss one? Okay, I missed one. Ah. How do I consolidate? How do I do it? Okay, we can turn off the bird cam because no. Oh, here we go. Debug console. Can I close that? I don't know. Yeah. Model. Failed to claim FPGA device mismatch between targets and ID code. Yeah, it's. Can see. Let me check if we forgot something. Constraints editor. Okay, let's check here. Oh, that's a lot of configurations. No. Shit. Wait. Oh, PNR, maybe there. No. Or I will switch to the 9K. I mean, I can still, or we do it in the IDE. If Caspar can find out how to use the 20K, we might want to unplug it. So stiff. The problem with the IDE that you need like a different programmer for the 9 and the 10 nanos. Yes, I try to implement that, yeah. Okay, let me try that and remove that, and we will try Teng Nano. So clock and let's. Okay. Let's store that and try to run that function first, and then we will see if it works with 20k once. Caspar. Hey, Mr. Who. Program. Yeah, we have. Oh yeah, we need to ZDIC it again. Which one do we need to change? Was this 0 or 1? Which one do we update? I forgot again. Oh, 0, okay. Yeah, I think the birds are done for today. I will switch the camera to FPGA mode here. Driver updates successfully. Oh. Ah! You were alive. You were alive. What does it do? Eh. Yes, tiny tape out in two weeks. We need to have a finished CPU. Okay, so is it too fast? LED counter, register LED. Okay, LED are never assigned, so what is the solution? No, what? Oh no, we need to call it LED. Let's just, that's a register. And then we will basically let assign let counter. That will be good enough, huh? I hope I'm still capable of doing. Okay, Caspar. So what's the solution? File, create project file. Where do I create? What? File, click auto detect. Where is auto detect? Auto save. No, what? Auto. Where is down there? Auto detect project. Oh, create a new project file. Ah. Ah, okay. And then something like that. Board, okay. Okay, and that's all. Okay, let's try with 10 nano 20K then. So back to 10 nano 20K. Okay, let's try again. So we need to change the constraints since they might not work. Yeah, oh no. Since we need to clock, let's add constraints. Oh yeah. Oh shit. Again. Okay. And this was one error. Or do you think this will work now with these constraints? I don't think it. I don't trust it anymore. Let's see. Error. Invalid device. Nah. Oh, I might need like to update that. Yeah. I need to update the toolchain. How does that? I mean, we can do it on stream. So how do I update the toolchain? Yeah, I know. Okay. Shit. Yeah. Yeah, you know what? I will go back to 9K because updating the toolchain in the Ubuntu. Yeah, let's concentrate on the work. Everything that doesn't fit on the 9K won't fit in the tiny tape out anyway. So let's remove everything and add the 9K here. Add from template clock and let's. Then 9K here, here, Okay, build and program. Okay, that works. Erase flash done, flash written, completed. Okay, now the problem is it's probably blinking very fast and we can't see it, so let's change the code slightly. I just call it counter because, oh well. Wait, that's the LED counter. Where's the clock counter defined? There is no clock counter. Where's the clock counter? There's no clock counter. Didn't complain. What? Where's the clock counter? I didn't How does this even compiled? Yeah, probably. But what I was wondering, why did it compile at all? I mean, it didn't have a clock counter. Did it just define it in place? Yeah, I added it, but here, register. Global FPGA white system variable. By default or what? On each clock. So why don't we see anything happening? LED's not changing. Auto created. Yeah. But doesn't do anything. Doesn't do anything. Yeah, but now we created 30. Oh wait, that's 33 bits register. Is it? Yes, yes, it was. Oh, sorry. I need to get used to Verilog again. Erase flash done. Do I invert? Does that not, or how bitwise invert in Verilog? Is this correct? Will that work? That's 10 nano 9K. What is going on? It should be at least inverted or anything. Tilde. Yeah, but why don't I see like errors, build errors? Do we need like to set the top module somehow? Oh, it doesn't count. It set just the one LED. Oh yeah, let's check CLK. From constraint, can I see the device? There is a way to... Hey PK, hey Matthias. I mean, oh, let's check with my old let's check one of my old 9K thing. Where are the files? CST. Okay, clock is 52. It's pull up. That's correct. Clock is correct. Yeah. LED is all right. I mean, button. Do we have SPA LED? Yeah, we can even drive it with 3.3 volts. Doesn't matter. It's pull up anyways, is it? Drive power unset. Let me check something. LED counter, and let's never change that. And let me change about that. Once that working, I guess it will go faster. Yeah, we can use system Verilog. I think it will automatically detect that. Will it? I don't know. Where's the setting for that? I'm wondering why one LED is lit. Oops. If we don't change anything and there is on positive edge begin clock counter +1, clock counter wait time begin clock counter 0. Yeah. That looks all right to me. No. Let's use ignore that. Hey, Lord. The project is about putting... So on the positive edge, okay, this works. So what we are trying to do is transferring my luniASM CPU design that we did on one stream to the FPGA to put it on an ASIC later. Okay, so what's the matter with that? Why didn't that work? Was it too slow? That's like 13 million whatever. Is this the clock speed? Would it increment like once every second or what? What's the issue? We shifted it now by 20 bits. Okay, how do you include a module? Do you adjust here? Let's do a new module, and then we call it CPU.v. Here we go, and then we use module definition as well. Oh. So we have input as clock. Yeah, and it will be automatically detected. So what do we have for memory interface? That's we can put LEDs there. Okay, let's leave the LEDs as the debug source, but then we have address. What's the address width? 24 bits. Oops. Oh wait. 27. Okay. Address. That will be output. Then we have in out. Can we define the width and make it abstract? I think there is a way of defining parameters, so we can make it like the bit size of the CPU smaller or bigger. Okay, let's start with 16 bits. That's basically data. That's the data bus, and we will have no. Oh wait, we are able to read any number of bytes from. Ah shit, maybe we need to put it like the data, put it like here. Oh, 8-bit data bus, because we can read, the CPU might want to handle like reading either 16 bits or 8 bits, everything possible here. Or 20, yeah, 32 bits. I don't know, I forgot how to use parameters. That was like a hash, I know it was something like that. How do you write that? So, first of all, we want to fetch fetch data. So this is the byte address. We need to read. We need a state. It's a state machine. So we have a register state. Do we? Let's do 0 read instruction that might be up to 5 bytes long, or if we do 16-bit CPU we can make it 3 bytes long. No, I think luniASM supports, so read instruction then we need reg. I think this needs to be a register. VHD. Hello Holden, it's Verilog. In-out data. I don't know how in-outs work in Verilog or on FPGAs. How do we manage that? Always. I forgot top. Always add post edge blah. Okay, here. Always add positive edge begin and oops, we forgot end module. And module, here we go. So end, not and. Here we go. Case, I think it was like that. State. How does Verilog case work? How European? In-out works only on external pins. Are you kidding me? No. Really? No. Are you kidding me? How do we transfer that? I mean, we are just passing them at some point. Okay, so we will do item single statement default. Okay. So let's do data in input. Yeah, okay. Data out. And that will be register. And then we need something like data ready or something. And case. What was it? And case. What do you mean with 2 lines of code? So 0. Read first byte of instruction. So we have register 16 bits. Wires, okay. That's in the top module then. You can't switch? Or are you kidding me? No. Yeah, I think that will be some sort of open drain mode or whatever. You can do out, and if you pull down, like, yeah, something like that. Okay, let's take care of the CPU first. And then, Ooh! Oh no! Let me move it over here. So this is not in my way. No worries. Do you want a code share? Where's the... Oh no, that's not the live. Oh no, what did I do? That's not... How do I share code? Share. Where is it? Live share. Share read only. Hi live. Not. I hope not. I hope not. How do I? Where's the link for live sharing? Where's the link? Oh, shared here. Okay, here is the live sharing link. Loop. Loop. I hope it's read only. We can check the CPU. What? No. CPU core. Okay. So we have Mesomosi, okay. Byte read address. That's the address. but I did it in comfortable language. This is more bits to send, data to send, clock, state load command to send, state init. Yeah, but it's also a state machine. So that's, oh nice. States are defined. Maybe we should also define it like that. So that will be paranoid about live share. State load interaction. Okay. Let's do it like that. Instruction pointer equals, it starts at 0. No! No, yeah. At the moment it starts at 0. But usually it should start at the address that we decide in our design. So the EEPROM will be mapped to somewhere else in the memory. Then we have the register stack pointer. Stack pointer, which is... Oh, wait. No. We subtract and it will wrap around. We'll subtract and then store. Oh yeah. You're right. You're a copy paste. I would figure it out quite soon. So now address will be IP. This will happen on positive edge. And then the CPU needs to be input. Yeah, you mentioned, but I didn't know what you mean. Data ready. Why is this? Oh yeah, I need to. Oh, it's 1 bit. It's 1 bit. Why is this blue? State. Yeah. State load instruction byte 0. Yeah, look, tabs. It's tabs. Oh no, spaces. Here, This is error on line 3 and error on line 8 now. Here, error on line 7, serious errors, spaces. So case, oh shit. Let me just do if data ready uh, 40 bits at most, huh? Oh yeah, wait. Instruction. We don't need to initialize that actually. Doesn't really matter. The state is the. Oh, we don't need to begin. The next case. Oh, sorry. Here, like that. Should I move it in more so it's clear? Is there a break? Is there a break? Do we need to break it? There is no break. That's Verilog. There is no flow. Okay. That's yeah. So instruction. Or let's call it 7 and an opcode. Opcode, okay? Oh yeah. Oh, I changed it anyways. Okay, so opcode data in state the fuck. Let me check something. Someone's writing me on Telegram and wanting to dox themselves. Okay. Let me just turn off Telegram here. Ah, why is this even offline? Okay. Oh, did I kick the device again? Here we go. So now we can identify the opcode. Yeah. Load instruction and then state analyze opcode. I don't know, Verilog extension. I have no clue actually. Let me do, maybe it's to Lushy Labs, maybe. I don't know, Verilog. Here. That's one that seems that's active here. Verilog, HDL, system Verilog, whatever. Blurry programmable. It doesn't focus here. State decode, what? State decode. Okay. State decode. Yeah, we will probably have more than 4 states. State. And I will call load opcode. Because the other we have intermediate values, that's all, or addresses. Load data state decode. Okay, that will be expanded. We have more states. Data in state decode. And this will be opcode. Yeah, so if we need to decide if there is more data to read, or how many bytes are there to read. So either we change the definition of our opcodes, so we see it's the first 2 bits show the length of the attached data, which will be a redefinition of everything, of our complete CPU. But it would be easier Hey Chris. Smoke editing, almost. We try to program it with the wrong byte stream. What if not more bytes are needed? Oh. So there are different, if it's, there is one opcode that's push. Wait. Let me open. Let me open our it's a stack machine, but push has there are different pushes that can have like 1 byte, push 1 byte, or on the stack. So we need to find out which push it is. Or we have a push with like 3 bits that identify how many bytes we push there. There could be a push 0 if we identify that would be interesting. So it converts. Hey, Mr. Johnny, you arrived. Where did I put? Where did I put my code? Where did I put my code? Let's save so I don't destroy anything. Open recent. IDE there. Oh, path does not exist. That's no good. Oh. My Google Drive is shut down. Here. Oh, it removed it from the old. Come on. Yeah. Okay, local param. Oh yeah, my description. Wait, I will find it. I will find it. Let me. I have it locally. Where did I put it? My search doesn't work, so my search are my eyes now. It's not that. It's not that code. Oh, this ass removed it from the recent once I tried to open it. Can find it. Oh, maybe the browser remembers. Let me check the browser. Where is it? Okay, I put it. Which project did I put it? It must be on my drive. And there oh, it's in the Megaplex folder. Yeah, I remember now. We made it for the Megaplex, didn't we? Yeah, here we go. Okay, let me put it bitluni's lab, Megaplex, and code and IDE. Ah, finally. Okay, I found it. Here. Yes, I trust it. I trust my CPP example. We can also use the implement. That's what is the MD load? Yeah, but that's not. What is the idea for stack operations? RPN? What is RPN? Push. Okay, 0 is push. So opcode push. Oh yeah. Yeah, but we are past that part. D8 0. That's the push. Then we have pop. So we have push B and push W 5 and 6. We might want to change that. Pop store. Wait, why that? Store. I don't know why I have 0 there. Store. Let me do a template first here, so I don't have to copy paste every single instruction. Okay. Store load push B push W clone loads, which will be bad for us. Loads stores swap. Then we have jump 0, jump not 0, jump greater, jump greater equal, jump equal, yeah, it is. Now these are the jump opcodes. Now we got to the ALU and or XOR not increments. I will just keep everything, and then if we want to optimize it, we can optimize it later. Function first. Hey Lucy. Ja, schon geschrieben. Wir machen den jetzt auf dem FPGA, die CPU. Sub. Then we have the shift operations. Let me put that. Shift left, shift right, mul, diff, which won't be implemented. Forget it. Also mod won't be implemented. That needs to be some microcode or whatever. I don't care. Neck. Apps. There is a knob. There is a knob. There is debug, and there is a knob. And this is basically 255. This is 254, and will be, and that one will be also basically a knob. ABS is 46, 45, 44, 42, 3. I don't know. Why not? Does it really matter? Ah, ja, das ist gut. Okay. Ja, das ist gut, weil den benutzen wir jetzt. So, a 30, 33, that's the OR, and 32. Yeah, that's 16. Oh, nice! Thank you, Lucy, for the sub. Yeah, and these are basically 2, 3, 4, 5, 6, 7, 8, 9. You know what's the worst? We need to decide. We need to decide how many words we will load on operations. So basically that will be like really bad if cases, I believe. Or we make it like beautiful and then I don't know. The worst one will be stores, which loads a value from stack and then loads from stack in the middle somewhere with a shift that it loaded. That's switch case. Yeah, we can do a switch case here. So, oh, thank you, Johnny. Hype train is coming. Yeah. There's so many subs. Thanks very much. Okay. We have now all the opcodes. Load. You know what's the worst? Push won't be implemented either, because that's like a Oh wow, bits, thanks. Because that's like a double word, and we don't have double words here. That will be a 16-bit. 16-bit for now. I hope nobody relies on the 32 bits right now. So even like the first one won't be implemented. So by default, we need to take care of load, push B and push W. So decode oh, wait a second. When we load the opcode, we can already use the data in as the opcode already. So we could decide here, after it was ready, we can already decide what to do next. So we store it, and then the state needs to be decided if data in, because at this we can save a clock if we can do it here already. Have the stack have associated flags tags, so you don't need. How do you push anything on the stack then? Ja, FPGA ist ein bisschen schwierig, weil alles passiert zur gleichen Zeit. Das heißt, es wird ein bisschen anders. Es gibt keinen diskreten Ablauf. Hey DIY. Oh wait. Yeah, no. Equals opcode. Push B. Then we need to load a byte. State decode, state load next, load byte. Yes, I must do that. So here so IP address, and then IP needs to be added here as well. IP okay. Redstone ALU, yeah, that's hard. Okay, so we know if it's or. No, do you use or like the keyword or was it in Verilog or? Oh no, I want only or. opcode out push W. This will be basically not there. It's not supported. So we decide now to load more data. And so this is what happens. The state, if we have a push, we need to get more data from the data segment. So load byte, maybe we need to trigger also set the address, because we have no trigger output load. Or read. Read, write. Okay, so we have reads. We need to set the address. Set the reads. That must be a register then. Read to 1 bit wide binary 1. And this needs to be rec. Does it need to be rec? Yes. 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 No, not really. It shares a bus. The address space is basically fragmented. So we need to load a byte. State load byte will be 3 then. Load, no wait, this is load opcode, and this is already decode. State decode opcode, and then we have, because this is already, we can save some cycles here. Decode opcode will be only processed when data is ready. So load opcode, let's copy that. Okay, so it loaded already. It caches it here. I will push it. Yeah. Tagged data instructions. What do you mean with tagged? What is tagged data instructions? Chris, I'm a noob in designing CPUs. I didn't pay much attention in the classes that I had on that. Ah, lost focus. Data. Oh, how do you store that? You have overhead everywhere then. With type on top of that, like visual types. What is a type then? Arbitrary data on the stack. Ah, okay. Okay. This is way too abstract. Lazy fuzzy logic moment. Yeah, we have mixed signals at the end. I hope that we can do a mixed signal with analog output. Lena, da ist ein Flash. Es wird drauf geflasht. Wenn man die Go-in, if you're using, I don't know, you probably understand. If you're using the Go-in IDE, you can, or the programmer, you can either write to SRAM or Flash, but usually it's written on the Flash. No, not now. We will do I'm coming from CISC. La Nea, what? Oh shit, Lucy, yeah. Sorry. Okay, I will call you Lucy then. It's this small on my 4K screen, your name here, sorry. Okay, so we identifying that we need to push more data and we can load byte. So we have here reg. We have internal registers. Let's assume we have two internal registers that will be, let's trigger a few people, AX, auxiliary, yeah, we will see what happens, okay? The worst is flip-flops, and we will probably run out of flip-flops quite quickly. So we will push. We could do a 24-bit. I mean 32-bit push here, but it will. If you do like a multiplication, the result could be 32 bits if you multiply two 16-bit values. So actually pushing 32 bits on a stack might be interesting. I don't know. It feels like a possibility, but let's not go too far here. Load byte. First of all, we will set AX 15.8. We will set that to 0. 8 0. Because we can have, we might not load more than 1 byte, and then we push 16 bits in that case. So usually we want to reset everything, or Oh, Casper. I don't know. I never tried, Lucy. I only, it's so fast, the uploading, usually with the other programmer, if you don't rebuild, you can have like multiple programs set up in the programmer tool, and then you just write the one that you want to be executed on the FPGA there. Okay, load byte, decode, opcode, and then data begin. Okay, now we need to change flash was. Yeah, you can always store like right to the SRAM and while you are testing, so there's no need to write to flash. If you want to have it permanent, you just create a I'll show it. Let me check. I will show you how that looks like in my. So if you are using the goins, the here it is. Okay, here. That's the programming tool. All documentation is on the SciPete. Yeah, so I have, you can see here, if I activate that, it will write this basically to SRAM, or I can activate another configuration that will program to the flash. So it really depends. That's just a programming tool, and that's with the Goin IDE here, Goin FPGA. There is, I think, an educational edition, but you get as a Hey Tilo. Tiluxi plays. Best viewers on. Oh, okay. This is spam. Anyways, you check out basically the documentation on the Tang Nano by SciPete. They describe how to set up the ID. Remove, nice. Okay, I think usually we would need to shields up, right, and then we will output rec. So basically we need to set, we set the address. Oh yeah, we set read, and then oh, if we read, if we put 1, then we won't be able to read the next byte immediately. So we need to have something set up here. Shit. Oh no. If we change the address now, wait. We might need to split that if state here. Uh-oh. I think I need to split that because we need to add a state loads byte word and d word here. Yeah, we clone that. I don't need that anymore. Push b load byte. And this will be basically in else case and else if. Is it? Else if? No, it's a make macro? No. Huh? Is there an elif in Verilog? And else begin. Else if begin. Okay. I know why and else if. Word, so we don't need to delete that. Yeah, we're not changing the whole thing here. Just trying to transfer it. We have 2 weeks for that. IP address needs to be incremented as well. Okay. It's still in the read state. Address changed. It will be, let's assume, so what needs to happen here, data ready needs to be or let's say expects to data be read in one cycle. if read is not cleared, load again. Okay, so this is clear. It's a little bit tougher handling, but saves another cycle. Okay, so load word, load byte. Load word, load byte. We do the following. State load byte data ready. It's also data ready. And then we have You're such a complainer, Chris. So always complaining. 9 days. Oh, really? Oh, shit. Oh, no. Oh, so we need to be done next week. Oh, no. Damn. How did I miss that? Yeah, if we can't manage this one, we will go on the next shuttle. Stack-oriented work. Yeah. Be open-minded. Be open-minded. Yeah. Yeah, weekends I'm gone now. Damn. So I will try next streaming more often next week, so we finish that up. Okay, so I will try maybe even Tuesday. Okay, so read needs to be and else. So and else begin. Not push opcodes. Okay. Not push opcodes, and then we have that's to do. To do. That's not opcode, that will be now AX. Oh wait, did I call it? That needs to be big. BX. AX. AX. Data in state push. State push. No, it's not RISC-V. It's some instruction set that we developed, that we came up with, reinventing the wheel. It's also open source. And we need to read is basically set it to 0 here. We are done. State push. So we need stay load word. Yeah. So what will happen right now is we will have state be set to that, data in will be set to 15.8. So, and the next byte will be reread. No, nothing special added. It's a stack-based CPU that we developed just for the fun of it on stream. In one like 4-hour stream, and now we just trying to make it run natively on an FPGA and ASIC. It runs in the browser already. It's on my GitHub if you want to check out. The idea was to basically implement this one time and write interpreter for every MCU that's out there that I'm using to not have to reinvent everything. Okay, so this is covered now. State load byte load. So we have the things implemented, the loading from the extra data. Now state push, which is basically, oh wait, there is no push. State push is here already. Oh no. There is no state push. That's happening on the same clock. We have the complete data here. State push is basically we are done. This is load opcode, and what we do is no, stack is always 16-bit. State write byte. No, push byte. Oh, let's do push 2. That will be for the second one. So we will that should arrive in like 10 days total. At least for me it was like that in Germany. So address data out. Data out is basically yeah, you're right, you're from Berlin. AX we store first byte first. Wait. No way. Wait. This is word. Oh. This is bad. I switched to big endian here. No, if we store word, we need to basically store it also Hameln. Oh, okay. How do we do it? We always load the lowest significant byte first. We need to rotate it. So LSB first. That's a thing here again. Okay, AX. Now we need to make a compound here, which is basically AX 70, comma. I think this is the way. And we can write, hello Z80, 8, okay. All right. Data out, basically data in. No. How do we do it? Peeps. Little endian. We don't know where we are coming from. If we store the word or a byte. Oh no, little endian is... Nice. Then you will be easy like reading the code here. Okay, so loading a word in little endian is hard because the first byte we don't know. Yeah, it's the lowest significant, but the second, oh damn. I have an idea. Good night, Jody. Why 6? 99? Why 6? No, this is wrong anyways. That's stupid. But I need like either, you know what, I will optimize later. I will do word 1 and word 2 and I don't care. Why 7 bits? 1 bit new? Oh no, we have 8-bit bus, Casper. No. The issue is, I will explain what the issue is. I wanted to reuse the same code. So we have the push, and then we can have either 1 byte or a word, and this is like little endian. So this is basically, so these are the 8 bits, and then we have maybe 16 bits, but this is 0 to 7, and this is 15. And if we have like now here, if we process, oh, it's a word that we want to load, so we would need to store this first and then know, oh, we read that here. So we really, what we really need to do is load word 1 and do basically the same, almost the same thing here. It really doesn't we can't do it like shifting here. Push B8. Or not even doing that here. Oh, what happened? Yeah, we need to distinguish here data in, and here that will be basically 8 bits. Binary 0. And then we have word 1, which will be data in, basically the same. Ah! Yeah, I know. This is a huge... Yeah, I know, but then the consequence after loading is something different. Word 2, because that's the highest significant data in. We have an 8-bit bus, which is really shitty to work with, so we need load. Yeah. We can simplify it without optimization to have like an intermediate clock somewhere, like always after something was completed, but then it won't be like super fast. We could optimize it later, like removing intermediate steps. So after we load the state, push to data out AX70. That's basically the same here. Copy paste, everything copy paste here. We write the first byte and then push 2 will be writing the second byte on the stack. This is just the implementation for handling the stack, which is Yeah, that could be a thing. But you need like to identify the opcode to know how many bytes to load and then push them on stack. I think what will crystallize is um, depending on the copy paste that we get here, we will see what kind of submodules we can extract from that and optimize it. Now I will just start with the push. I think the push will be one thing like pop and push from the stack will be the most commonly used one, so that might end up being submodules. The parameters, like 16-bit parameters. This is what's happening right now. This is like, it can be 1 byte, 2 bytes, or 3 bytes. Usually it's 1 byte in this 16-bit version. In the 32-bit version, it could be also 24 or 32 bytes. I think there is no 24, but make it a flag. So many. Okay, if data ready, if data ready data in ready, we need to change that. Data out ready. So we need data ready. What? Data out ready. So since we are writing now, so read and yeah, I know, but in that case it's only one opcode. Right. One read push begin and write B1. Was Lee 16 push, B32 push? What do you mean? You load it in the high register and a high. Yeah. The register isn't actually transparent. So what? Oh, what? No. Oh, big endian, little. Yeah, but then I have like two registers. Okay, this is not what we are talking about. I mean, I have to handle little endian in some way, or I switch to big endian, what I really doesn't want to know. Yeah. Peeps, no changing right now. The only thing that we want to do is to finish it. No advices except for Verilog right now, or how to change this code. No, how to change everything. All right. So AX 15.8, and this is basically, we have push to that's pushing on the stack. So we are done here, which will be right here. Right is 0, and data out right. Oh no. No. We need state finish. State finished. Then we need to stack, the address needs to be set there as well. State finished begin. No, data out ready. Push second. That will be basically state push done. Push done. Done. Maybe we change it. State. No, it's not YAML. Load opcode, and right will be 0. 0 and okay. So this is writing. Let me now finish that. I need to concentrate. Sorry, I will answer your questions in a minute. Data out. Now we need to set the address as well, and we need to set right here. Word 1 byte, say push to. So here, and the right needs to be set here as well. Let's copy paste, which I don't really like, but we need to do it. We need address, stack pointer, -2. It will be 16d2, and then we'll set stack pointer, or let's do uh, 15 0. There's no way this will work. SP and N SP SP SP. Okay. So what happens now is we decrement the stack pointer by 2 because the stack is always 16-bit wide. Then we write the address where to store the first byte. Oh, foo. Yeah, so the second push we will do this. Yeah, it's fixed with. Oh no. SP. No, +1 because we need to store it. We decrement the stack already here. Push done. NSB. No, not. We are at 16 bits right now. I would love to have it 32 bits, but it will be too big for the tiny tape out. We will change it at some point. Like after we made some experience with that one, we will optimize it and make it work later. State push 2. Push 2 will be here. So data out. Now we will have address and no SP P1 P1. That's not the new stack pointer P1. That's basically because the higher the high byte needs to be written to higher address here, but the stack pointer is already at its position. Data out, right, and that's right. Stack-based processor, yeah. Okay. I think we stored everything. So what we can do now is we can push 1 byte or 2 bytes on the stack. That's all we can do right now. Yeah, not happening. The extra slow then. Identifying first before we continue. We have that already with this push thingy here. Okay, push done. Push done. Oh wait, we are already in here. 5, 6, oops, 7. We are already at 7. Might chain. Yeah, I think we need more code, more states. State push to yawning. We can find out. Wait, push to push done. Load word 1, load word 2. Oh. Let us find out. Yeah, we would need to instantiate it, and then we need like to connect everything. That's let's just. This is probably already like 30% of the CPU. It's pushing bytes, reading bytes, and pushing bytes. We don't have a pop yet. The pop will load bytes from stack and increment the stack again. Load opcode. We load opcode from the code segment. Load bytes to where? So we have SRAM and we have EEPROM. We have instruction pointer and the stack pointer. Stack pointer is in SRAM. It will start at 0, so the wrap around and the stack top will be always on, like the first push value will be on the top of the 64 kilobytes or whatever it is. Yeah, it has to be there. And if we make it less wide, like the address space here for the SRAM, it will end up being there, because I think we are using, yeah, that's 8 kilobytes. What's the width of the data of your ALU? 16 bits. It will be 16 bits, the ALU. Multiplication will be tough, so that will be many loots if we don't do it sequentially. We can do it sequentially. Bottling. I mean, we can instantiate it if you like. Top V, let's do it. Let's do it. So once. Sorry. Short intermezzo. Yeah, really? Yeah. Multiplication. Okay, now we have the issue that, let's say we have CPU. Let's put a CPU here. Passing stack positions. Yeah, we always popping the top of the stack except for stores, which is taking a value from the stack with an offset, because otherwise it would be almost impossible to work with that. We would need like a swap or something on the top of, I think we have even a swap that switches the two values on the top of a stack. So yeah, how do I instantiate a module? Module my design and module, and then my design D0. Oh, so you do like CPU and then, okay, so let's do it like that. CPU, let's call it like that. So, and then yeah, this is how you wrap it. It won't know. CPU is basically, let's copy that. Read data in, write data out. Oh yeah, I think I will remove the LEDs from the CPU. We don't need them here. How do you call the part that manages the bus? The bus, let's call it the bus. Bus driver. So what we will have here is output. This whole stuff is really not interesting. Let's move it down. In let's call it like that. So wire Moldiff is a repeat count. I mean, that could be an implementation. Multiplication could be okay, how do you do Verilog in out? What is this? Go F yourself. I don't want to load for half an hour. Wow, forums. Input outputs. What is this? Input, output. In out by dear. Oh, we can call it in out. Oh wait, I can't call it in out. NP output. Oh, that's interesting. Output enable, and that you can have a Z for high impedance. That's cool. Okay, now I got it. Out P A B. That's cool. Okay. B is bidirectional, always construct. Okay. That's a good example how to use that. So if it's in input mode, job, native bytecode, Java bytecode. Yeah, that's cool. Stack-based processor. Have you a link, Bob? I will give you the I will give you mod rights so you can paste the link, Bob. That would be interesting to see that one. Oh. Not Stack Machine. I want the code, the open, the specific open source implementation for that job. Okay, so output enable in out IO, this is input, this is out input, whoops. Put output. Job design. Nice. I'm a little hungry now. Okay, how do we use it? How do we use it? Clock will be CLK. CLK, that's easy. Address will be, that's easy. Address low. Address, let's do that. Address high. We need a new state machine here as well. So reg state reg state, let's say it's also whatever 0. We might want to do 3B0, and then we do the following. We will connect the lines accordingly. If data out, let's do state, case state, because we need to know in which state we are. Let's call local params here. It's unfortunate that we don't have enough address and code lines and whatnot. I think my TTS died. I can't hear it. Yeah, TTS died. Hey Joachim. What are you doing in the chat, in TTS chat? Bitluni TTS join. Here we go. State load set address idle. No, we need an idle state. State idle. Or yeah. Set address 0 idle write address 0 write address 1 write data then write done. Oops, what do I do here? This is not a value, this is a value. Nobody says something, or I can't hear you because of TTS. Broken. Okay, here we go. Wait. This is also broken here. Nobody said anything. Ah. Shit. How often did I... Every constant here is badly syntaxed. Yeah, the size of the count of bits first, then the type of data that's following. Here we go. So this is decimal. Oh, come on, the stupid, how do I, wait. Okay, here we go. D, nice. Here we go. Yeah, I just used Alt and mouse. Alt and mouse click. Worked as well. Nice. Multi-line cursor. Alright, I fixed it here. What is this? There's also, there's so many typos here. Yeah, that would be caught hopefully on compile. Okay, so state data done, then we have read res 0 read res 1 read data, I guess read done. Okay, let's see if that will work out. We need all the stupid states here. 6, 7. Okay, we have all the states for handling the stack. Now case. Thanks, Bob. System Verilog has Anom. Thanks, Sonic. I will... it will probably... Is it by default supported by users, or do I need to like specify it somehow? Yeah. Enumeration. All right, I'll keep it like that for now, and we can optimize the code later. Now it's even done, so I will push it in even more. So what we will check now is wire write. Wire write, wire read, and this is read. Right. So read dominates. If read, then we will read the address. And we don't need to store it. We will have the wire address wire 15.0. Let's just basically put here. That's flip-flopped anyways within. Then we need to set output enable. We have a wire res latch 0 wire at equals out. Let's do basically out 0. Nobody cares. And address latch, that's out 1. Then we have SRAM output enable. Oh, it's 3. Oh. SRAM read enable, write enable or something. Yeah, let's read and write. I think oops, 2, 3, 4. And then there is SRAM chip enable is this node output chip. We have no MUX for now, so we will ROM, or we can do RAM here and here ROM. ROM read 3, 4, 5, 6, and this will be, we will change that at the end, so no worries. Wire no, assign. Wire is basically a direct connection, like a wire. So these are always the same values. I don't know. I think we can do it like that. Use toggle. They are different. They are not toggle because we write to latches. Show you the design. Didn't you study the design? We have the latches for the address bus here, and we are basically latching in the address. So why? Oh no, we could do toggle because output enable actually activates it or not. Usually we don't even have it like that, so we might want to put it also in the upper bits of the address. We don't know yet, so that's just work in progress. So let's leave it like that. And then we have data in, data out. Two wires, read for RAM, output enable. Yeah, they're using that. Two wires. Direction at strobe, what does that mean? Read for RAM output enable and write for RAM output. The current FPGA is the 10 nano 9K. Oh, we also tried the 20K. And yeah, but this is just for testing the design. Yeah, that sounds, strobe sounds like some sort of latches or so. No, wait, strobe was in multiplexers. I saw that one. We can check the datasheet for that. I mean, it doesn't matter. I just want to strobe is chip enable. Yeah. Whatever. Let's continue. I mean, the actual how we will actually handle it at the end. I just want to wire everything up so it's theoretically working, and then we can physically test it with actual devices. So if we read state clock line of, yeah, something. Is there pen or paint paper here? So these are latches for the address, since we have only like 8-bit I/O here and output and inputs. We are using for address lines, we're using latches, which can be selected, and then and then we can have basically either we manage internally the mapping of the ROM and the RAM in the address space, or the higher address lines address either ROM or RAM. So we can have that covered with upper bits of, okay, this is now 24 bits. But if we have like 64 kilobytes, like C64, we could map the ROM and the RAM to some regions of the memory. So there wouldn't be necessarily, yeah, chip enable and then write and MMU. What is MMU again? Address and then read address 0. Let me finish the state machine here, as long as I know what I'm doing, because we don't have much time left. Oops. Yeah, that's what we are doing right now. We can test like with, we could even have like more chip enables and have extra RAM for the stack or something, like an extra chip. So the design isn't like fixed for now. So what do we want to do? We want to have data IO oh wait, IO needs to be what was there's like, how was the IO again? Oh damn, I forgot it. Input assign bidirectionally. Okay, here. So we need to do something like that. Bidir assign IO, and then we do basically, if we have anything read here, state reads inputs is basically state as I think this is the only thing that we are reading. Yeah, we don't have that. We have always read and write. There is no inverted. If it was inverted, like either read or write, like not read and then write, and you can attach it both to like the same line. Yeah. That's what I also have. Assign IO is input is basically 8Z, otherwise now we can map here output byte. Yeah. Output byte is here rec. Yeah, it has, but this is the FPGA, the ROM of the FPGA is for the FPGA. We are simulating a standalone CPU which uses different code, different ROM, and it will be on ASIC without any ROM included. So we need to have an external ROM that we will use for code. Output byte equals 0. Okay, so output byte will be basically, output byte will be set to to address low, then data in ready, data out ready. Okay, wire data out ready. No, this is rec data in ready. Now this is strange because we need to count clocks. We can't have like maximum clock cycle here while setting output or input. But this will be something that we need to do later. This will be specifically for the ASIC. So yeah, we need to wire data out. Data in ready. Oh. Data out. So data in ready is 0. Oops. Because we are setting the address data ready, and then we need to set the latch, which will be address latch. Address latch 1, address latch 0, one. We can delay it or whatever, but in that case, state idle, state oh, we are in read. Good night, Kasper. I won't hold you back. I know you need to brush your teeth. Bye bye. Address high. Okay, we need to set address and then set address, read address 1. We will set this latch as well. And we will have SRAM. No, this is read. We can do read ROM chip enable. No, we will just do RAM chip enable. RAM chip enable equals 1. RAM chip RAM read RAM write. So this is what's happening. Chip enable read And then what will happen in the next iteration? Read done. Ja, bestimmt. Also du kannst bestimmt auch irgendwie einen Teil des EEPROMs damit benutzen, aber ich will jetzt nicht extra das machen, vor allem seriell dann noch den EEPROM da versuchen zu teilen und was auch immer, wenn ich das sowieso anders machen will. Also ich will ich will es ja extra standalone machen. I want to do it standalone, that's what I'm saying here. Not using the RAM of the FPGA, I mean the ROM of the FPGA. It's the same with the SRAM. I could use block RAM for that. But here we go. Santo. A cure for ginger people. What? I didn't know that ginger people needed some cure. I recommend listening to Aurora, Cure for Me. I think it's called the song. Yeah. Oh no, this will be terrible. Yeah, I was even on the concert of Aurora when she was in Berlin last time, or I don't know, was it last time? It was right after the pandemic. Aurora is really great, one of my favorites. Singer-songwriter. Beautiful voice. If you know Aurora, you probably also know Fever Ray. She had a band formerly. She does solo now, but she was in a band called The Knife. Also really cool, from I think also Norway. Oh shit, yeah, sorry about that. It was really great. I had like to grab, since my girlfriend didn't want to go, I had to grab a friend who wasn't even a fan, Dave Darko. But he enjoyed it. It wasn't like it didn't have goosebumps like I had, I think, once goosebumps in the concert. But he enjoyed it as well, so I had to force people to come with me to the concert. Okay, so this is the read state, but we don't have now. Oh wow, nice autograph. Yeah, it is. So read done. This is just copy paste. Now I'm confused. Okay, read done is basically we can set the state to state idle. I will I will do a output byte. Wait a second. We can set the, we can call it data byte or bus byte. Okay, address low, address high. Wait. Why do I have second state? No, read done here. So read done, and then read done will be basically no address anymore. Wait. We write address high. There is no bus byte. Latch. Yes, this is Verilog. Then bus byte. A reg. I need an in byte. Oops. Cached in byte. That's. I think I need to make it a wire in the CPU. Read done. So cached in byte will be IO. Oh wow, there was a commercial with that song. The first time I saw her was, I think she was invited as a star, a guest star on a ceremony of Nobel Prize, some ceremony or something. It was also running with the Wolves. Yeah, I think it was like a Nobel Prize ceremony, prize giving or whatever, and she had a, no, before that I saw even one concert on that was a YouTube channel. I didn't know, like, it was just a random concert from a random singer-songwriter back then, but after that I just remember that I watched a complete concert of her. Yeah. All right, so cached byte, and what we do basically, we also do, no, wait. Yeah, cached byte, and then cached in byte will be here. Good night. Yet next week we need to be done next week, so we will be testing, and as soon we see first good night, Lord. Fax where? What? No, not really, Bob. Kraftwerk, I mean, that's like a standard, an old standards that are running. Flexware, yeah. We are trying to ban the CPU that we stack-based CPU that we designed on stream into FPGA to put it on tiny tape out on an ASIC. I think data in is input. Wait, it's not a register. Nice. Okay, so we can data in cached in byte. That is all right. And then RAM chip enable RAM read RAM write state read done. Yeah, I think there might be many nerds, but I must admit, when I was on a concert from Aurora, it was like 80% women. So actually, not that many fans, male fans there. Which is a hint to the guys: go to Aurora concert and you can meet some girls there. Here we go. Data in ready. We need to set it to be 1. Oh no, that's true. Most of them were very alternative, not really FPGA. Are they into FPGA development by any chance? Nana Lufthansa. That's really old school. That's before my time, really. I don't know. I'm like, I mean, I either listen to music that's quite old, like the music that my father like taught me or showed me when I was a kid. So more like Pink Floyd and Deep Purple, stuff like that. And then 80s, 90s. So Massive Attack. Massive Attack was like my favorite band. Also Radiohead. I got my tinnitus from a Prodigy concert, but I'm not listening to them anymore. Chemical Brothers. I was more into electronic music back then. And of course, like I like all the demo scene tracks, mod tracks, STM tracks from the 90s. I think I even had mod tracks from Westbam, which was really crazy. Cover from Teardrop? No, I don't know that one yet. But I was like Massive Attack. I was fan, even like when they started, they were not really known. And I had like an compilation album where there was like Unfinished Sympathy was on there, and I loved them from the start, from the beginning, and I got like every single CD from them. Another band, which is a terrible name, they called Transmission. If you look for Transmission, you will find many trance stuff, but that's like world music. They play didgeridoos and instruments like clarinet and so on, and they're so good. That's I love also world music. Hey, Yombo Prime. Okay, I will check out the cover version of Teardrop. Rob Hubbard. Who is Rob Hubbard? Need to check them out. Is this also an artist? What bands did I listen to? Yeah, much chill out music. Klaus Schulze, Jean-Michel Jarre, Klaus Schulze. Bob, maybe this is something like, do you know Klaus Schulze? Or Jean-Michel Jarre? Everyone knows Jean-Michel Jarre. He was like an icon back then, similar to Kraftwerk. C64 musician? Rob Hubbard? Yeah. Phonotronics, they made music with with Game Boys. Yeah, I think Phonotronics was a band that also made music with chips. Oh, also Console, the band Console. I heard many things from them, which is also like electronic music. Oh man, there's a lot. Anyways, let me just try to wrap this up here. Data in ready. We don't have data out ready here. Or data out. Wire. We need a wire here. Wire 70 data out, because this one isn't set yet. So let me finish that. We might want if, else, if, write, begin, and okay, so we have a state where we write something to an address, which will be write pass byte address hello data in out ready. We can move that outside here, I believe. We could move it outside. Address latch. No, if it doesn't do anything, we don't need. Okay, address latch 0. That's the only difference here. Right. Right address 0. All right, and then we only considering SRAM for now. I think my TTS bitluni just died. Yeah, bitluni left. Know why? Oops. Okay. Daft Punk Moby. Very influential hip-hop music. Kraftwerk. What? All right. And Lucy, you can always like talk to the people on Discord or wherever. I mean, all the nerds are here. Right. write down. So we do write address. I hope the optimizer will find over. Oh yeah, might be that. Unexpected maker, Mr. Sion. How is your robot arm? Does it work? I'm curious. I didn't watch your stream. Yes, right here, right now. He is very, very famous here. Africa Bombata. Yes, I know. Yeah, yeah. I will know that. Fatboy Slim is also like Moby. Africa Bambata, I know that one. ARM is not finished. Been working on my Milo Mill. Just assembling the enclosure. Why? What is a Milo Mill? Never heard of that. What is that? Oh yeah, I need to set both bus byte output. Okay. So open source minimal. Read and write and ship enable. You know what? I think this is easier than, we don't even need set idle ready data out. Ready. I think this is all. You know what? The first compilation. Oh, we didn't specify top. We didn't add Tang Nano 9K. I need the pin configuration here. No. Oh man, this will be a lot. In okay, 0. In 1. Into and 3. Four and 5 and 6. Yeah, I know. Sorry, I can't change this either. I can do it like that in 7. I didn't specify the location yet because I'm just defining the in-out ports for that are on tiny tape out. Where is it? Oh no. I think all right. I mean, very busy always. Can't complain. You probably noticed like one of my videos here and there. And I'm doing too many things like the Asic stuff and trying to pull off the mega clusters and hustling here, but really I don't know. I should clone myself to be able to finish all the projects that I started. How is your company working? I mean, your business, Sion. Are you happy with the current state? Or just soaring mode right now? Do you have employees now? I don't know really. I didn't get an update for a long time, I believe. You had employees, didn't you? That help you out. I don't know. I very careful not spending as much as usual. Good. Okay. I mean, so if you're not overworked, that's a good thing. In one way, so you can work on, let's say, prevent the burnout that was hovering above you all the time. You were overworked all the time. I believe there are many boards right now that are competing with your stuff, aren't they? I mean, you have like accessories for your ESPs and so on, but there is so much stuff pushed out right now. I wouldn't be able even to try everything that's out there, like TTGo and all this M5 stacks and all those types. So many RISC-V MCUs out there now. So I mean, ESPs are still mega, but I don't know. Is it only my impressing? Not underworked, super competitive market and hard to get seen. Rap about finances, so not really finances. I mean, inflation hit hard, I must admit. Like salaries didn't go up, but expenses went up like 50% since COVID, which is really terrible. So probably that's why there's no spare money anywhere. Yeah, also on my side, since I bought this house, I have no spare money at all. I have to pay back my family because they gave me a small loan. We didn't have any bank loan or anything for that. Cost of living, utilities, expenses. Yeah. Oh shit, yes, double definition. Yeah, I didn't pay attention. Thank you. That's I/O. Oh, what? Yeah, you need a novelty. You need a novelty, Sion. I don't know. What's with the H5 or what's the newest CPU from or MCU from Espressif? Make it really like the newest shit. You just need to be first to the market. If you don't have like how are you build game consoles or whatever, I don't know. It's hard. Okay, select IO pin. So why aren't they named? So let me check. I will Nano 9K. I will check the pin out. $3.3 volts. All right. Oh, there are 3 banks, but one bank is only, you can see 1.8 volts. So let's set the output bank to 1.8 volts. What are those colors? I can't tell the colors here. So IO 70 12B, IoT 12B. How do I set that? Location. Oh, wait. Wrong side. 79. Yeah. Okay, 70. No, that's out 0. 79 in. Here's something else. Out. 283 4 85 86. Okay, input bank 1 will be 51. Wait, is this also bank 1? Both are bank 1. Where are the LEDs? SPI, LCD, no, RGB. $69, $70, okay, 51. So I could actually use 51. Wait, 51. 51 to 70 here. 51, 52, 53. $56. $8. 58. Wait. Yeah. 59. I go there. 59. 60. Wait, here. 60. 61. 62. 63. 64. 5. Wait. That's wrong. That's 50. And that one starts at 70. 51 and 70. Oh, come on. Wait, no, 49. Huh? What is this bank? Damn, 70. Oh, shit. Okay. Yes, I am making an actual CPU. And I hope to have minimal external components, so like 4 or 5 components, active components like RAM, ROM, multiplexer, or oh wait, yeah, I need some latches for the address, unfortunately, because there is only so much space. 77. Okay, here we go. Now input ports. Input ports will be this blue bank here. There's plenty. Look at that. That's, yes. The luniASM instruction set, which is on my GitHub. We made it on stream, and now I'm putting it to Asic. It's very flawed right now, but it works. If it works, it works. Ship it. Wait. Where's Mozi Mizo? That's another one. Oh, foo. Okay, 40, 35, 40, 35. Okay. Where is it? Where did I start? 29, 29, 30. No worries. Not much missed there. 334. Then we have 40. 40. Then we have 35. What you know what? It's the same for me for your project. I only hear from Johnny that this you try to assemble your robot arm, and after the stream it was less assembled than before or something. So a lot of printing, was it? How far are you? How many joints are missing? Okay, I think we did it. Let's run the toolchain. Build and program, run it. Syntax error, what? CPU 5. What? Oh no, that's frustrating if you don't know where the error is. But it sounds sounds like you're having fun with all the toys for men. Lucy, I'm doing YouTube in out. No, it's actually input output. It's both. But the problem is line. Oh wait, do I need to put rec? Is this the order? Oh yeah, okay. So rec needs to be inside here. Input, output. Sorry, my syntax. Here we go. Token ID CPU 45. 45, yeah, there is a stray D. Oh, wow. Too compact. Jumbo, you are following all the streams. Are you a regular to see on streams? I think the toolchain completed. I don't know what it's doing here. No, wait, error. Foo. 39. But we are proceeding here. 139. Nice. 39. Huh? Oh. Wait, you don't do semicolon? Or what? Oh, yes, it's working. Okay. Number of wires, memories, 300 cells so far, 340 cells. Oh, flip-flops. Oh, a lot of flip-flops here. That won't fit in a This will not fit in tiny tape out. Even like that one. Shoot. Quite some loots, but that isn't bad. Tasks finish with errors exiting. Toolchain completed. What are the errors? Oh, where did you see that? Oh, here. Okay. 58. Where did I want? Oh no. No, that's GoWin FPGA. 68. It's 68. 68. So 50. It's 68. Here we go. Build it. Do it. Run it. It's the 10 nano 9K in that case. I want to switch to 20K, but we were not successful using it before. I think, oh yeah, I need to update USIS for that. For the 20K. With errors again. Oh, CLK. Oh, that's very helpful, this error message. Anyone, is this like, did I reuse a pin somewhere twice or what? CLK is 52. Oh yeah, 52. Shit. Okay. Oh, come on. Which pins didn't I use? Where's 52, by the way? How did I use it? There is no 52 here. IO1. IO0 is 51. Ah, shit. There is no 52. Oh, come on. 3, 4, 5, 3, 4, 5, 6, 7. 6, 7, 68, 8, 69. Okay, last try. It's almost 1 o'clock and I want to watch Dark Matter. Did bitluni die again? No. Oh, you're doing GPU? A rasterizer or what kind of? So you're making a rasterizer there? So are you using floating point units or are you using like fixed point arithmetics? What is the? I found a book. Today I found my first book where I learned how to write a rasterizer. This must be really hard. Are you using like fixed point? Okay, nice. Yeah, and do you have like lookup tables for sine and stuff like that? Arcos tangents. At least you need sine, a sine table. What kind of FPGA are you using there? Something went horribly wrong here. Oh. Different modes for the same pin set. Here, 3, 3. CMOS type, but I mean, what? CMOS type. Will it take it? I hope it takes. Can I edit the constraints in text? That would be probably a little bit easier to copy paste. I also might need to that's way too. Number of cells 341. Might be too many. Yeah. That's taking default CMOS there. Oh, foo. Oh, we can select from the top module. I didn't see that. Yes, it is. Especially if you have so many pins to specify. The problem is I don't know what I actually need, because we have like something pull up and I have nothing specified here. The open source tools might be a little bit complicated to It worked! It's done! Okay. Okay. Device utilization. Ground 100%. GSR 100%. I have no clue. Slice 2%. VCC 100%. IOB 11%. I don't know what is this. IOB. DDR, everything zero almost. Great, yeah, that's a start. I mean, there is so much missing. We don't have a single opcode. Okay, you know what? You know what? We can do, we will implement a NOT. Like inverting, oh no, we don't have a push there. We can push. We can pop and pop, oh, we don't have pop implemented. You know what? That's still a lot of code to do. I think next week we will stream more often. I'm happy that it compiled. It will probably never fit and tiny tape out. It will be really tough. I can try to set up example project to make it build and see if it compiles with tiny tape out. So we see the utilization. If I want to use analog pins, I need to take 2 tiles anyways. So I would aim for 2 tiles there. Yeah, machine code will be written by this device to this EEPROM here. And this EEPROM will, so the CPU will read from the ROM, and then, yeah, we have that. I ordered also this is the SRAM, and this is the ROM, the EEPROM. And I have plenty because we were doing the C64 projects, so we used parallel SRAM and ROM already. So that's convenient. I need to check if I can find the latches, but I think I had latches here. Oh, this is Skywater 130. Check out tiny tape out. Here. Okay, text specs. No. Asic facts. Does it even say? Oh wow. If that closes in September, April will be the next shuttle. So we really need to commit to Tiny Takeout 7. Or we will do as EFAB less a whole ASIC for ourselves. So that's the open wait. Chip ignite. Let me zero it out. Parts per design. Yeah, you can check that out. Anyways, thank you everyone for joining the stream. Yeah, we discussed a lot, had a long intro, and now we need to really push that forward next week. I don't think I will make it on Monday, but I will try to stream on Tuesday, Wednesday, Thursday, and Friday or something. Yeah, I think I can. Yeah, even. Is Friday the 1st? No, Saturday is the 1st, so I think there is like the deadline or something. So see you next week. Bye bye everyone. See you. Have a good night. I will stream on all days. And not only one day, I will stream several days next week. No worries. You will catch an update there. I really want to try to get the something on Tiny Tapeout. So how do I end the stream? There is no way for me ending the stream. Anyways, I will just start.